Here we go. So don't, yeah, of course. Okay, listen up. So don't, well, not even there anymore. There we go. Okay. Okay, listen up. We're actually starting now. My PowerPoint crashed for a second there. Don't worry about the Chapter 19 thing. That's not, well, you gave your books back. Oh, speaking of that, if you have your book, just go ahead and put it on my desk right now, okay? If you don't, well, I'll tell you what. Listen up. If you have your book here at school, just not in this classroom, then talk to me after we get done with the notes for today. I want you to go grab it, okay? Because I need those books by the end of the week. Yeah. Okay. So the last thing that we are going to talk about this year, the last new thing we're going to talk about this year is acids and bases, all right? This is a fairly relevant concept. A lot of the things that you deal with in your everyday life are either acidic or basic, and that can affect the way that they interact with you. So we've dealt with acids in this class, so I know you've had exposure to it at least in here, but I think you've had more exposure than maybe you're aware of. Okay, so acids. We're going to talk about acids first. Acids will taste sour. And some of you may be thinking, who would taste an acid? Well, you do all the time, okay? Yeah, oranges, lemons, any citrus fruit, really, okay? And then a lot of other types of foods also are a little bit acidic. Now, the citrus fruits are very acidic. That's why they taste sour sometimes, okay? But you're eating something fairly acidic when you eat a lemon or a lime or an orange. Okay? They will cause blue litmus paper to turn pink. That probably doesn't seem all that important to you. We'll do a little work with indicators probably at the end of next week so that you can see how different indicators work. There are several different things called indicators that will basically turn different colors based on whether they're in an acid solution or in a base solution. One kind of interesting one is cabbage juice, okay? Which I don't know why you would ever need to know that, other than it's just kind of interesting. If you boil a cabbage and you use the leftover juice, that cabbage will turn certain colors based on whether it's in an acidic or a basic solution, okay? So cabbage juice is kind of a natural indicator. Acids will conduct electricity. So whatever you do, don't take a bath in hydrochloric acid and drop a toaster in there, all right? For several reasons. They will have a pH below 7. Yeah, we're going to talk about pH, all right? So by the end of this, maybe not by the end of this week, but definitely by the end of next week, you will know all about pH, all right? But right now, you just need to know it's pH below 7. 7 on the pH scale is perfectly neutral, okay? That's the pH of pure water. Anything below 7 is going to be acidic. Anything above 7 is going to be basic, all right? Oh, from your pool, yeah. Yeah, if you have to pay attention to the pH of your pool, then you even probably know some of the ways that you can change the pH. Yeah. Okay, so bases are kind of the opposite. Bases taste bitter. Now, you've probably had less experience tasting bases because the most common bases you would have in your house are cleaning products, and you shouldn't be tasting those, all right? One that you may have tasted before is baking soda. Baking soda is basic. Some people brush their teeth with baking soda, or there's some baking soda in your toothpaste. Now, if you just have a little bit of baking soda in your toothpaste, they probably put some other stuff in there to mask the taste. But if you tasted just straight baking soda, it's fairly bitter. Yeah, it doesn't taste very good. Bases feel slippery, okay? Stuff like soap, a little bit basic, right? Soap is obviously very slippery. But most bases, when you put them into water and then you feel them, they will feel slippery. They'll cause pink litmus paper to turn blue. So again, that's the whole indicator thing. Okay, certain indicators turn different colors based on whether they're exposed to an acid or a base. Bases conduct electricity as well. And we'll talk about why in a couple of days. All right? So those are the major properties. Oh, and a pH over 7. I already said that, but there it is. Okay? All right, so now we get to do something kind of fun. Not really. No, I'm sorry, I was being a little sarcastic there. We need to learn how to name acids, because there's a special way to name acids. So now we get to go back to the naming stuff, naming and formula writing. Okay? I promise acids and bases will get more fun next week, but we got to do this first, so that you know how to name them. Okay? So acids are compounds that form H+ when they're dissolved in water. Okay? That's going to be kind of the definition that we go with here. So when you put an acid into water, it will increase the H+ concentration, which means that it probably had an H to begin with. Does that kind of make sense? There must have been a hydrogen there on the compound in order for it to give an H+ to water. So you're going to notice the formulas of acids usually begin with H. Not always, but they usually begin with H. Okay? In order to be an acid instead of just a gas, binary acids must be aqueous. So most of the acids we're going to talk about are solutions. Okay? Now there are other definitions of acids where, you know, the acid could actually be a solid or a gas. But we're going to talk about the ones that are solutions. Ternary acids are all aqueous solutions. I don't care if you know that. So let's talk about some examples here, okay? HCl, hydrochloric acid. Notice the H, right? That's your biggest clue that this is probably an acid. HNO3, that's nitric acid. And H2SO4, sulfuric acid, okay? So notice, all of these start with H. Now this one has 2 H's that it starts with, so it doesn't just have to be one, okay? But the acids that we talk about in this class are pretty much going to start with an H, so that's how you can identify them. That's pretty easy, right? Okay. So binary means that there are 2 elements. You guys remember that from when we were naming before? Binary ionic compounds means that there's just 2 things. There's one cation, one anion. Okay? So if you have a binary acid, then that means that there's just 2 elements. There's H and then one other element. Okay? If you have a ternary acid, that means you've got a polyatomic ion in there. It's H and some polyatomic ion. So let's go back here for a second. Which ones on this list are binary? Just the HCl, right? You guys see that? Because there's hydrogen and then there's chloride. Those are the only 2 elements there. The other ones are ternary because I don't feel like I'm pronouncing that right. Ternary? Ternary. Let's go with ternary. Ternary? I don't know. Anyway, whatever it is. The HNO3 and the H2SO4, notice there's a hydrogen and then there's at least 2 other elements there. Okay, so those aren't binary, they're ternary. I'll just go with that for pronunciation. All right, so that's the idea there. Now, in order to name these, it depends on whether it's binary or ternary. Okay, you have to decide, and once you decided that, there's different ways of naming these. Okay, so if it's binary, that means the anion ending would just be IDE. Okay, so for example, HCl is just chloride is the anion, right? It's just IDE for the ending because it's just chlorine by itself. So the way you name it is with this. You put a hydro. Yeah, that's a children's book that I wrote for PBS. And as soon as I pick this up, it's going to go back to it, isn't it? No, I guess not. Okay. So hydro is the prefix here, and then you put ic acid at the end, and then what you put in the middle is whatever the anion is. All right? So the anion for HCl is chloride, right? So you put the chlor, CHLOR, in here, and you end up with hydrochloric acid. You see how that works? Okay? So it's all based on the anion. These take a little while to get used to, so, I mean, we're going to do some practice today. Ternary, it depends on whether the polyatomic ion ends in ATE or ITE, okay? If the polyatomic ion ends in ATE, like the two examples on the page before were nitrate and sulfate, okay? Let me go back to those for a second, okay? This is NO3 is nitrate, SO4 is sulfate, right? So those both end in ATE, those polyatomic ions. Then you just drop the hydro part. It's basically like this, except there's no hydro in front, okay? So then the HNO3, that's nitrate, so it would be, whoops, well, I'll just write it up, the whole thing out, nitric acid, right? Okay, so you just do the nitr part and then put the ic acid on the end. What would H2SO4 be? SO4 is sulfate, so this would be, well, and then it's kind of like where do we end the stem, right? It seems like sulfuric acid would make the most sense. That kind of sounds weird, though, doesn't it? So sulfuric acid is how we name that. If you said sulfuric acid, I would not count that wrong. That's just knowing where to break that prefix off, okay? But it is sulfuric. Actually, I probably would count sulfuric wrong because we're going to talk about that one so much that you should know that one, okay? If the polyatomic ion ends in ITE, okay, which you're going to need your polyatomic ion charts again when you're doing this today. But if it ends in ITE, then instead of ic acid, you put us acid. Okay, so an example of that would be if I had HNO2 instead. NO2 is nitrite, okay, instead of nitrate. So this would be nitrous acid. Does that make sense? It's all just based on whatever the polyatomic ion is here at the end. Okay? All right, easy way to remember which goes with which on the polyatomic ions. In the cafeteria, you ate something icky. Ate ick. All right? I ate it, it was ick. So then you can remember the ate and the ick go together, and then hopefully then you can remember the ite and the us go together. Oops, my cookies are done. I don't really have cookies. I have something in the oven right now. That's what the timer was for. I need to reset it to remind me to take this stuff out of the oven. Let's do 20 minutes. Okay. It's just some chemicals. It's not interesting. It's not food. Sorry. If you ate it, it would be icky. See, brought it back to the notes. All right. So here's a flow chart. Sort of how you can think about this as you're naming these. An acid's going to start with H, so that's how you're going to know it's an acid in the first place. Okay. Then you ask yourself, does it have 2 elements or does it have 3 elements? Okay. If it has 2, then it's hydro and then ic. All right. Hydro, whatever the anion is, and then ic at the end. If it's 3 elements, that means there's no hydro prefix, so then you have to decide, is it going to be the ic ending or is it going to be the us ending, and that depends on what the ending on the polyatomic ion is. Okay? All right, so let's do some practice here. HBr. Let's look back at our chart. First of all, it starts with an H, so it's an acid, right? Whoops. Oh, you already have those? Oh, you don't have those. Okay. Well, we'll just do these together then, okay? And then you can start writing down some of the other ones for practice. So HBr starts with H, 2 elements or 3 elements? 2, right? All right, so we're going to put hydro in front of it, ic at the end, okay? So how would we name this thing? Hydrobromic acid. Actually, I think this is already written on here. Yeah, it does. A lot of these acids are going to sound weird to you. You just got to get used to it. Hydrobromic acid, okay? So that's it. H2CO3. Okay, now we have to be careful here, all right? There's no hydro because there's 3 elements, right? So then we've got to decide, well, what is CO3? And this is where it would probably be a good idea to have those polyatomic ion charts out, unless you have this memorized. Okay, CO3 is carbonate, all right? So because it ends in ATE, if you look over here, say it again, carbonic acid, okay? No hydro prefix, it's just carbonic. When it's binary, that's the only time you put hydro in front. Yep. Okay, and then H2SO3. SO3 is sulfite. Okay, so sulfus I would accept. Technically it's sulfurous. Okay? Just remember it was sulfuric. So sulfurous with the OUS. Alright, you see how that kind of works? It takes a little while, like I said, it takes a little while to get used to that, but that's how it works. Okay, now we're on the ones that, nope, we're not. Oh, okay, alright. Okay. Alright, so now let's go the other way, okay? So hydrofluoric acid, let's figure out what the formula for that one would be. Okay, first of all, hydrofluoric, is that binary or ternary? That's just 2 elements, right? Okay? So H is going to be the first one. On any acid, you always put H first. What's the second one? This looks like fluorine, right? So probably HF. Okay? Now, you kind of have to do these like the ionic compounds. You have to think about charge. All right? What charge does H usually have? 1 plus. What charge does fluorine usually have? 1 minus. So it's just a 1-to-1 there. So it's just HF. Okay? H plus, F minus gives you HF. Right? Does that make sense? Okay. So then sulfuric acid. Okay, so we have an H, obviously. Is this binary or ternary? So what do we need to be looking at right now? Probably the polyatomic ion sheet. If it has the, and you just have to go backwards here, if it has the ic ending, that would be sulfate, right? Okay, so you need to look at sulfate. Sulfate has what charge? 2 minus. Okay, so you've got H plus and then SO4 2 minus, right? So then what would the formula be? H2SO4. Yeah, that works. All right, and then nitrous acid. We already did that one, didn't we? Oh, we did nitric. Okay, so there's 3 elements there, obviously, because there's no hydro in front, so it's ternary. But this one ends in us, so the polyatomic ion would have to end in ITE. So what is the polyatomic ion here? Nitrite, okay? Which is NO2 1 minus, so then the formula would be HNO2. All right? You okay? Okay. Oops, what happened? There we go. Okay, so now I think these are the ones that are, yeah, these are the ones. Okay, so I'm going to give you a couple of minutes. I'll just pause the video here. I'll give you a couple of minutes to work your way through these, see if you can figure them out, and then we'll talk about them together. Okay? All right, ready, go. Okay, let's go ahead and talk about these, see how we did. Well, maybe. Come on. My computer's being really slow. I hope it's getting all the audio here. Okay, so HI. You scared to say it? Okay, hydroiodic is how you would pronounce that. Yeah, you have to be careful with that one. Okay. Hydroiodic. Okay, it's just weird. It doesn't look right, you know. But you know the hydro needs to be there. You know the ic needs to be there. So then it's just a matter of figuring out exactly where to put them. Okay. HCl we already know, right? but now it makes sense, right? We've been calling it hydrochloric acid all year, and now we know why we call it hydrochloric acid, okay? H2SO3, sulfurous, which we actually did that one already, didn't we? Sulfuric acid, HNO3, nitric, we already did that one too. And then HiO4. Was that one on your polyatomic ion chart? Okay. This is periodate, okay? So you would call it periodic acid. It does. It looks like periodic acid, but it's periodic is how you pronounce it. It's the same way. Yeah, but this is iodine, and it's periodate is the polyatomic ion it comes from, so you'd call it periodic. I got it right. I don't know. You don't have to know how to say it, right? There is not a pronunciation part of the test. Okay, now we need to write the formulas. Well, we already did hydrobromic too, didn't we? HBr. Sorry, there's some repeats here. Nitrous. HNO2. Carbonic, we're also, good grief, need to figure out some different acids here. Okay, here we go. Phosphoric. Not sure what you just said. Okay. All right, now this one we may have had some trouble with, right? So let's talk about this one. Phosphoric, okay, first of all, binary or ternary? Yeah, this is more than 2, right, because there's no hydro in front of it. So we're looking for a polyatomic ion that ends in ATE because of the ic ending, right? So we're looking for phosphate, probably. Okay? So phosphate is PO4 3 minus. So we know we have our H plus. We've got PO4 3 minus. So when we write the formula for that, it's going to be H3PO4. You crisscross. Yeah. Hydrotelluric. Okay, so you'd have to figure out what telluride is first. But this has got the hydro in front of it, so that tells me I should be looking on the periodic table. This is just one thing, right? So tellurium becomes telluride, or I guess telluride when it becomes an ion, right? So then it's H plus, and then looking at where TE is, it's number 52. Do you guys see it up here? Okay. What charge would that one probably form? 2 minus because it's in group 6, same group as oxygen and sulfur, right? So the TE is going to be a 2 minus, so then when you crisscross your charges on that one, H2TE, okay, which looks really weird, but that's what it is. Okay? All right, now as far as bases, I just want to mention this. We're not really even going to do any practice with base naming because you don't need to. You already know how to do this. A base is a compound that will form OH minus when dissolved in water, or depending on your definition, you could also say it accepts an H plus ion from an acid. Okay, the bases we're going to look at in here, for the most part, are going to have OH on them, so that when you put them in water, that OH minus comes off. Do you guys remember what OH minus is called? Hydroxide. Okay, that's a really important polyatomic ion because it's kind of the one that determines whether something is basic or not. Okay? All right, so formulas of strong bases are going to end with OH minus. So those are going to be easy to identify because they'll have the OH at the end of them. So any compound that we have named or written a formula for already this year that had the OH minus in it, those are bases. Okay? So you've been naming and writing formulas for these, you just didn't know it. Bases are usually dissolved in solution. Whoops. Is there anything for you to write there? Okay. It's already there. And since the bases are ionic compounds with OH minus as the anion, or sometimes they're molecular compounds, you don't need a special method for naming these. Okay? So for example, NaOH is just sodium hydroxide. We already knew how to name that, right? Because it's just the sodium and the hydroxide. CaOH2 is calcium hydroxide. NH3 is just ammonia. That one is kind of that's one that we normally call by its common name. But if I was going to name NH3 the official way, what would I call it? NH3. Do we know if that's ionic or covalent? It kind of looks ionic, but when you've got a hydrogen with a non-metal, when the hydrogen comes at the end, then it's usually covalent, okay? So NH3, I think we've written the Lewis structure for NH3 quite a few times this year, haven't we? Looks like this, right? We only write Lewis structures like that for covalent compounds, okay? So NH3 is covalent, which means that if we were going to name this thing, it would be nitrogen trihydride. Remember that? You have to put the prefixes on for covalent compounds, okay? But it's ammonia, because that's a common name for it. Okay, so that's the base nomenclature. So what I'm going to do is give you a practice worksheet on acid naming. The answer key is on the back of the worksheet, so you can check your answers, but I would do several of them before you check, okay? First thing tomorrow, we'll have a quiz on naming and formula writing for acids. And maybe we can do the testing today. Yeah, I want you to take some time to practice these. Maybe in the last 5 or 10 minutes I can do that, okay? Okay. All right, let me turn off the video.